While studying kinematics, we saw that we could use math to predict the motion of an object. We could figure out where it has been in the past, where it will be in the future, how long it took to get there, and even how fast it was traveling. What we were really doing was analyzing how an object was moving. But why was it moving in the first place? In other words, what is it that causes an object to speed up? The answer is surprisingly simple. The only thing that can cause an object to accelerate is a force. In this video, we'll look at how forces influence the motion of different objects, and we'll challenge our intuition of how things work in the physical world. Here is a wooden apple, resting on a countertop. Before seeing anything else, you've probably made a number of assumptions. We rightly think that the marble counter is heavy and rough, and that the apple is smooth and light. Say we plan on giving the apple a shove to the right. We all have an idea of how the apple will slide and stop. And thanks to our intuition, we can make predictions like this on a moment-to-moment basis without much effort at all. But what if it were possible to remove everything that our intuition is based on? What if we could remove all the air in the room, which can cause air resistance? Remove all the friction from the ground and walls, and remove the force of gravity? Now if we pick the apple up and let it go, it won't move anywhere because there's absolutely no forces acting on it. If we bump the apple now, would it ever stop moving? The truth is, once we give the apple a bit of velocity, it stays at that velocity, moving in a straight line until it's bumped again. This isn't just an imaginary experiment. It turns out that this is exactly what happens in outer space. But before we go any further, let's look at a little history. The first person to make this claim lived over 300 years ago. His name was Sir Isaac Newton, and he was a brilliant scientist, brave enough to challenge our intuition about everyday physics. Newton's goal was to figure out how the world around him worked. He had the thought that everything we see follows a few simple rules, which when added together, build up to explain the complicated physical interactions all around us. Newton's predictions are now known worldwide as Newton's 3 laws of motion and are used when dealing with anything that moves, from cars and trains here on Earth to spaceships that fly to the moon. At the start of the video, we asked the question, what causes an object to speed up? Newton answers this question in his first law of motion. An object with constant position or constant velocity will remain at that position or velocity unless acted upon by a net external force. Well, this is just reiterating what we already realized. The only thing that could cause our apple to accelerate was a force. So what is the next logical step in understanding why things move? If we now know that a force causes acceleration, we might also wonder how much acceleration we can get from a certain force. The answer to this is actually Newton's second law of motion. F is equal to m multiplied by a. This means that if you want to speed up an object by a certain amount, you will have to adjust your force depending on the mass of the object. Heavier objects need stronger forces. Let's look at what this math means in real life. There are 3 variables in the equation, so we'll look at 3 examples, each with one variable held constant. But before we start, let's bring back gravity. Okay, first let's hold the mass constant. Let's bring in 2 toy blocks of the same size. This part is pretty intuitive. If we gently push the first block, it'll accelerate slowly. But if we push the second block with twice the force, it's going to accelerate twice as fast. What if we were trying to push something much heavier, like two large masses? Now our robotic arm has to push at 100% of its strength to move these objects. And when we push the heaviest mass, it's a big struggle. But when we push the smaller heavy mass, even though we're pushing with the same force, we can make it move faster because it's lighter. In our third experiment, let's drop a hammer and a feather from the same height at the same time. What does your intuition tell you will happen? Most people imagine the hammer hitting the ground first, because it's heavier, so it falls faster. Let's try it out. They hit the ground at the exact same time. Amazingly, humans have actually done this experiment on the moon, and it turns out that our predictions are completely correct. Let's look a bit more at this third experiment, since its results are a bit unexpected. If the acceleration of the hammer and feather are the same, then what does that tell us about the forces and masses? Well, we know that the hammer has more mass than the feather. So that means that for the math to work out, the force of gravity on the hammer must be more than the force on the feather. So we know from Newton's second law that the hammer and the feather fall at the same speed, because even though the hammer is pulled with more force, it also has a greater mass. So in the end, the ratio of force to mass is the same for the two objects. This is why they fall at the same rate. What we have just stumbled upon is actually a very important distinction in science. The force of gravity acting on an object is known as its weight, which is not the same thing as the object's mass. You can think of mass as something that belongs to an object no matter where it is, whereas the weight of an object changes depending on the gravity of the planet that you happen to be on. In outer space, your weight would be 0 newtons. But since acceleration is constant at 9.8 meters per second squared on Earth's surface, we can use the force of gravity is equal to the mass times the acceleration of gravity to quickly find the weight of an object from its mass, or vice versa. For example, the weight of a 10 kilogram mass on Earth's surface is 10 kilograms multiplied by 9.8 meters per second squared, or 98 newtons. So now let's look back and try to explain why our intuition was wrong. What goes on when there is air resistance that makes the feather fall more slowly? Let's look at the feather on its own to start. We just found out that the feather has a small weight because it has a small mass. So this means that the force of gravity pulling on the feather is relatively small. So let's draw a small arrow to represent the force of gravity acting on the feather. What other forces are acting on the feather? Well, in a vacuum, gravity would be the only one. But with air resistance, there is actually a second force acting on the feather, in the opposite direction to the force of gravity. For a hammer and a feather, the force of air resistance is nearly equal. But since a hammer has such a larger mass, the hammer barely notices this small force of air resistance. For most calculations in high school physics, we deal with objects that are large and fairly heavy, so you can usually ignore air resistance. But for a feather, it makes all the difference. The analysis technique that we have just used is one that you will use all the time from now on. The use of arrows to represent all the known forces acting on a single object is called a free body diagram. For problem solving in physics involving forces, you will almost always start by drawing one of these. On that note, we are now completely ready to tackle Newton's third and final law. So far we have answered our two biggest questions. First, what causes an object to accelerate? And second, by how much does the object accelerate given a certain force? It might seem like we have asked the two most important questions, but Newton thought of one more question to answer, which most people might not have thought of. The first two laws are centered on an object that is accelerated by a force. But what is providing the force in the first place? Newton's third law is that there is no such thing as a lone force. All forces come in pairs. In technical language, for every action force, there is an equal and opposite reaction force. Let's look at some examples. When a robotic arm pushed on those masses as hard as it could, the masses were actually pushing back on the robotic arm with the same force. When the Earth pulled on the hammer as it was falling to our studio floor, the hammer was actually pulling back equally hard on the Earth. But since the Earth is so large, we don't notice the Earth accelerating towards the hammer. And as you sit in your chair pushing it down with your weight, it pushes back on you with an equal force. You wouldn't even be able to walk if Newton's third law weren't true. When your shoes push back on the ground pushes forward on your shoes, and this is the only reason you are able to walk forward. Okay, let's take a breather. We've now covered all three laws of motion, and there were probably a few things we covered that didn't immediately make sense. Let's look at a generic example involving forces, and use Newton's laws along the way just to solidify our understanding of everything so far.